Okay, ladies, so hopefully you got on well with those. So how to do titration calculations using the correct formula. So this is our formula that we use here. Now they are trying to push you away from using this formula. So they're changing the structure slightly of titration questions when they give them now. So don't be frightened by that. You can still use this formula, but it may involve jumping a number of steps. Okay, we did practice that before we finished up, and I will do an example of that a little bit later on in the video. Okay, just remember V is volume. So how much of if it's Va, it's the volume of your acid. If it's your Vb, it's your volume of your base. Ma is the molarity, the amount of moles per litre, very important, okay? And N is obviously the number on front of the balanced equation. You will always be given your balanced equation in your question. Now, what glassware that we need? Okay, so you've got your burette, obviously. Okay, this is your burette here. Okay, you've got your conical flask there. Okay, your burette is designed specifically to ensure that you've got it's calibrated to ensure you've got your tap full. So you have to always have the tap full there. So when we're filling our burette, we always fill above 0 and we let it run down to 0 to ensure that tap area is full. With the burette, you always rinse with deionized water, then the material it is to contain to ensure it's not diluted. With your conical flask, you simply rinse with deionized water. Okay, and then we have your volumetric flask. This is a very, very accurate piece of glassware that is designed for you to make up a solution up to the meniscus. So that is what we make up our standard solutions in, and that's what we do our dilutions in when we're talking about your vinegar. You always have to use your funnels, but always remember to make sure that you remove your funnel from your burette prior to using it, because that can increase the volume slightly if the stem of the funnel is sitting in it. Okay, so that would be a mistake in your calculations if you did that. Then you have your pipette and your pipette filler. Again, that's a safety feature that's sometimes asked in questions. Why is it necessary to use pipette filler? Well, historically, we used a mouth pipette, okay, and that was even before my time, which is a very long time ago, okay? So obviously that could be dangerous because you're pipetting up acids and bases. So we use a pipette filler now. Your pipette should be rinsed first with deionized water and the material it is to contain first as well, okay? Remember, deionized water is just used to prevent any kind of side products or anything forming, all right? Now, what a primary standard is. So a primary standard is a substance that can be obtained in a stable, pure and soluble solid form so that it can be made up into a solution whose concentration is accurately known. This is called a standard solution. So your primary standard in this case, girls, is sodium carbonate, anhydrous, which means without water, sodium carbonate, anhydrous sodium carbonate. A standard solution, then, we've said it in the last slide, girls, is a solution whose concentration is accurately known, and they are made from primary standards. Now, you've also got things such as secondary standards and tertiary standards. That is when you are working out the concentration of something against a primary standard. Now, how to make up a standard solution. Again, I'd like you to pause the video to see if you can remember at least 4 steps of making up a standard solution, and we will do it again in a little demonstration now. Hi ladies, so we're going to be talking about standard solutions here, making a standard solution, because it's something that comes up all of the time and it's usually a 12 to 15 mark question, so it's well worth knowing, okay? So if we're talking about our primary standard here in its volumetric acid-base topic, okay, it's always going to be sodium carbonate, anhydrous sodium carbonate without water present, okay? So first thing you're going to do, I spelled that wrong, weigh out your anhydrous sodium carbonate on a clock glass. Remember there, those curved pieces of glass, so piece of clean clock glass, okay? Then you transfer to a beaker and dissolve fully using a wash bottle of deionized water, ensuring there's no traces of your anhydrous sodium carbonate left. Then you're going to take a funnel and you're going to transfer it to a volumetric flask along with all the washings. The washings are simply the remainder of the deionized water that you're kind of ensuring that all of your anhydrous sodium carbonate has transferred into your beaker. So they're the washings there, okay? And then you make up to the mark in the volumetric, ensuring that the meniscus is sitting at the line. So you need to be at eye level to ensure that's done, and that's usually done with the wash bottle first of all, and then when you get close to the line with a dropper, okay? And then finally you have to homogenize your sample by inverting it 20 times with the lid in it, okay? So that is how you make up your standard solution. Thanks, girls. Now, little details to remember, girls. Our original primary standard is sodium anhydrous sodium carbonate. Okay, so that's a common question that they ask. So what, how did you work out the concentration of hydrochloric acid solution? We used anhydrous sodium carbonate as our primary standard, because it's available in solid form. It doesn't lose water over time. It's not going to sublime off like iodine does. Okay, so it's a pure, stable solid. Hydrochloric, then our second experiment. So our first experiment was making up our primary standard solution in our volumetric flask. Our second one, girls, is the titration against hydrochloric acid and sodium carbonate. Now, girls, this hasn't come up in a long time. It's usually on an ordinary level paper because it's quite an easy one, okay? And here, when we work out the concentration of hydrochloric acid, it becomes a secondary standard, okay? Then we take our secondary standard, our hydrochloric acid, and we titrate it against sodium hydroxide, in the process making sodium chloride. Now what we do here is we do our 3 titrations. Okay, remember the first one's a rough titration, the second 2 are accurate, have to be within 0.1 centimeter cubed of each other. Then we do a final titration, a 4th titration without any indicator, using our average titer. Okay, and then we are able to evaporate off the water and get a pure sample of sodium carbonate from that. That's the little detail you need to remember about this experiment here. Again, this hasn't come up in a very long time as far as I'm aware, so be one maybe to look over. Okay, it's an easy enough titration, but it hasn't come up in a very long time, and it does come up on ordinary level papers more often. Ethanoic acid, your vinegar experiment, girls. Okay, so here we are taking sodium hydroxide, which is now a tertiary standard, and we're titrating against ethanoic acid. Now here we do a dilution of ethanoic acid. So usually take 25 centimeters cubed of ethanoic acid and dilute it up to 250 centimeters cubed in your volumetric. That is a 10-factor dilution that you'll have to take into account at the end of your calculations. Now, all of the indicators we use for each of our different titrations are methyl orange, except for ethanoic acid. We use phenylphthalein as our indicator. Okay, so just be aware of that, girls, and you need to know the color changes for each one of those. Okay, so remember, this one goes from colorless to pink. Methyl orange goes from what is it? Methyl orange again. Sorry, it goes from yellow to red in color. Okay, and finally, determination of water of crystallization and of washing soda crystals and the value of X, girls. So this is probably the kind of doozy of all of the titrations, because this is kind of hard, calculate the water of crystallization and your value of X. So I'm going to put in 2 examples of how to do this percentage WV for your vinegar, and also this one here, crystallization of water and your value of X. I'll put in a little sample question at the end here. Thanks, girls. I hope that's useful. Hi ladies, so I'm doing 2 questions from your workbook, and they are just, I suppose, 2 of the tougher kind of calculation acid-base titration questions. So the first one is a vinegar sodium hydroxide titration. Remember, this is not asking this question, but this is the titration where we use phenylphthalein as our indicator, so it's slightly unusual. All the rest are methyl orange, all right? Now, the other unusual thing about the vinegar titrations, girls, is that you have to work out percentage weight per volume at the end, okay? So looking at 13.14 in your workbooks, girls, so you might want to have a little go at that yourselves, and maybe pause the video now and see if you can get the same answer as me, okay? Now, so I've put in my my volume of my acid, that's my average titer, is 20.25. My value of Na is 1 because there's 1 on front of this. My concentration of my base is given in my question. It's 0.15 molarity, which is moles per litre. And my volume for that is 25 centimetres cubed by pipette. And then our NB is 1 as well, because there's 1 in front of this in the balanced equation. Put this into our normal titration equation, what we get is our concentration of acid is 0.185 moles per litre. Now remember, that's our diluted sample. Now in the question it says that you are taking 50 centimetres cubed and you're diluting it to 250 centimetres cubed. That's a dilution factor of 5. So if we're after working out our diluted sample concentration, we're going to have to multiply that answer by 5 to work out the concentration of the original vinegar. All right. Now, so when we do that, we multiply this by 5, we get 0.925 moles per litre. okay? Now it asks you in a question, and they will usually lead you through the steps that you have to go through to get the answer, to work, calculate it in grams per litre. So you multiply that by 60, because we're trying to work out your grams per litre, so it's your moles by your molecular weight of your acetic acid. So it's 0.925 by 60, and that's 55.5 grams per litre. Now we need to convert that to percentage WV. Now remember what percentage WV means first of all. So percentage WV means weight per volume, okay? So remember, we need to work out the grams in 100 centimeters cubed of our solution, all right? Now if we know there's 5.5 grams, 55.5 grams in 1000 centimeters cubed, we just need to divide that by 10 to work out how much is 100 centimeters cubed. So that's all we need to do there. So if we divide that by 10, we're going to get 5.5 grams per litre, or 5.5 percentage WV. So that's our answer there. Thanks, girls. Now, our other question that we're going to do is 13.16, okay? Now 13.16 is meant to be representative of your sodium carbonate, calculating the percentage of water, and also calculating the value of X. Now here they're using another type of acid called oxalic acid, alright? But it's done in exactly the same way. So you run through your normal titration calculations as normal, okay? And you get 0.049995 moles per litre. Now you can just round that if you want at this stage to 0.05. Now I haven't, just to ensure I don't have any rounding errors, but it's no harm in doing that there at this stage. So that's the strength of our oxalic acid per litre. Now they're asking us to work out our percentage of water. Now they've told us at the start of the question that we weighed out 6.3 grams originally of our oxalic acid. Now when we work out how much what the mass of that amount of moles is, because we just need to multiply that by 90, which is the molecular weight of our oxalic acid, we get 4.5 grams of oxalic acid. So that's quite a big difference in weight. So we weighed out 6.3 grams originally, and we're shown to have 4.5 grams of oxalic acid present in your titration. So the difference there, girls, has to be your percentage of water, or your amount of water in grams, okay? So that means if you take these two values away from each other, your original amount, and you take away your calculation amount, okay, from your titration equation, you get 1.8 grams of water being present. Now you have to work out what percentage that is. So 1.83 grams of water, okay, 6.3 grams is the original weight. So you, just like a test result, girls, you put 1.8 over 6.3 multiplied by 100, and that works out to be 26.6% water of crystallization. And your value of X is slightly more difficult. We are told in the question that oxalic acid has a formula H2C2O4.XH2O. And we have worked out that 0.05 moles has a mass of 6.3. This is your value from your titration calculation, okay? This is your moles per litre. I've just rounded up to 0.05, and this is the weight they told you you've weighed originally at the start, okay? Now we have to work out what the mass of 1 mole is. So all I've done here, girls, is I've divided 0.05 into 1 and find out how many times it goes, and it goes 20 times, a lovely round number, okay? So if I multiply across here by 20, I'll find out what the mass of 1 mole is. So that's what I've done. The mass of 1 mole is 126 grams. Now, we know that the mass of 1 mole is the overall weight of the molecule, and we have the molecule formula here, okay? So this has a mass of 90, water has a mass of 18, and we don't know what the value of X is. So essentially it's just a little quadratic equation there to finish it off. So to put that in there, girls, we get X is 2. Okay, so I'm hoping, girls, that you understand those steps there, and if not, let me know and I'll do another one. Thanks, girls.